Okay. All right, thanks everyone for coming. So today I'm going to talk about a kind of medium-baked set of ideas that I've been thinking about for a little while now. A way to do a one-point statistics version of a cross-correlation. So I'm going to explain what that is, but first I'm going to start with explaining why that's a thing one would want to do. This is not like a finished process in any way, shape, or form. So I welcome, you should be doing this that way, or other comments along those lines. Because this is definitely at the interesting idea stage rather than the formally correct statistical analysis stage of the process. But I have a set of data I'm hoping to use it on in the near future. So this talk is a nice way to actually, put the ideas in order for that process. So cosmologists, I'm on the cosmology half of the CCPP. Cosmology to 0th order is the study of density fields. I measure some fluctuations, delta of X, somewhere out in the universe. And, I do statistics to figure out what physics is governing the evolution of the universe. So the kind of most generic cosmological procedure is I measure a density field. This could be the fluctuations in the brightness temperature of the cosmic microwave background. This could be fluctuations in the density of high redshift galaxies. It could be gravitational lensing. It can be any number of things. But usually what I will kind of generically do is I will Fourier transform this field because, density fields tend to evolve via gravity. Fourier transforming takes a bunch of coupled differential equations and turns them into uncoupled ones, at least when everything's linear. I measure some Fourier transform, delta of k, and then I will almost universally construct something called a power spectrum. Usually we construct these fields in the context of fluctuation analysis such that the mean is 0. We usually deal with the mean in other ways. But so we write down an estimator, the expectation value of the variance of that density field. And this is an object we call the power spectrum. So in cosmology, the universe is on large scales isotropic and homogeneous. It's basically the same everywhere you go in every direction you look. So this quantity can't depend, this quantity can't look different if I have two k vectors pointing in opposite direction. It has to look the same for all k vectors. And so you get some Fourier constants that cancel out, you get this delta function, and you are left with this object called the power spectrum.
And that, and when you said that, this is you're in theory land right now, right? Because
so this is probably what I was about to say.
Okay, fine. Yeah,
so in theory land, this object, this expectation value, is an expectation value over an ensemble of universes. The initial density fluctuations that source all of these things come from this period of inflation at the beginning of the universe, where in the current model, they are all sourced by basically the Heisenberg uncertainty principle. So they are truly random. And so the inflation model predicts an ensemble of universes, which we average over to get this power spectrum. But because we made this assumption that the universe is basically the same everywhere, in practice, we can take an estimator for the power spectrum, where we say, if I have Fourier space, K and Kx, Ky, say this is 0. Because the universe is homogeneous and isotropic, basically any k vector pointing in, with the same length pointing in different directions should all have the same statistical properties because the universe is the same everywhere. I can rotate the universe by 180 degrees and it should all look the same. So in practice, what we do is we take, I'm going to put proportional to because I don't feel like remembering what the constants are. In practice, we can make a measurement of a density field, take the variance of all of the density modes in a spherical shell in K space, and the expectation value of this estimator is the same as this theory space ensemble averages of universes.
Where the spherical shell has a finite K thickness and is.
Yes, I mean, in principle, if you were, had a perfect measurement of everything, you could take everything down to a, infinitesimal shell. But in practice, yes, you have a finite K thickness, and then there's an error on this estimator that depends on the number of modes in that finite width shell. But at the end of the day,
number of modes has something to do with your survey volume.
the number of modes has to do with the volume you surveyed. Exactly. And so you put all that together and you get an estimate. And this is, this is a very well understood process. You can write down the errors on this thing very well to extremely high precision. This has been used for everything in cosmology for a long time. It's fantastic.
Question?
Yep.
So when you do this Fourier transform, do you do it in flat space-time or in a curved space-time?
So it depends on exactly what you're trying to do. For the probably the most famous power spectrum is the cosmic microwave background. And for that, you're actually doing a spherical harmonic transform on a sphere. Sometimes you care about relativistic effects, and you have to take your Fourier transforms in a relativistically covariant fashion. Sometimes you can just say everything is acts like flat co-moving space because my volumes are small enough. There are an endless, there are very simple approximations that theorists will write in their idea papers. There are very complicated forms of it that people will write in actual precision cosmology papers. But yeah, sometimes you have to do relativity.
But just following that question, in the case of a survey like BOSS or whatever, is the volume big enough and the redshift space large enough that you have to be careful about how you do that Fourier transform? I think it probably is.
Very much, yes. Sometimes, so like if I'm surveying on a sphere, this is a really bad way of drawing a spherical shell. Sometimes if you're surveying on a sphere, you have to deal with the fact that like your line of sight vector is this way over here and this way over here, and then you either have to split up your box, which limits your ability to do large scales, or you have to do, replace this this Cartesian Fourier transform I've written here with something involving Bessel functions.
But it must depend on what Ks you're interested in, because like on the VAO scale, like I don't think any of those analyses have to deal with the relativistic effects.
Yeah.
At least at the precision that they currently are. I don't know about.
But there's growth of structure effects as well.
Yes,
Sometimes-
sometimes.
in that direction.
Yeah, sometimes,
Yeah,
so
is-
usually, so sometimes you'll split this up in the line of sight because things are evolving. Yeah, so
Or
this
you could
is-
do a transform to get it into some consistent coordinates and then do it in that.
Yeah, exactly. There's a ton of, there's a lot of detail you could go into on here. But at the end of the day, what it all, at the level of detail at which I'm going to care about it today, it all boils down to take a piece of space, do something approximating a Fourier transform at it, and then take the variance of it. So the nice thing about this, this statistic is if I have a zero mean field, and if the statistics of that field are Gaussian, if it's a Gaussian random field, so the probability distribution of the values in that field are Gaussian distribution. The power spectrum contains all of the information in that field. And an easy way to understand that is, if I have a Gaussian, it's entirely described by its mean and variance. I've said it has mean 0. This is a variance. Ta-da, we know everything. And a lot of cosmological fields are like the CMB is almost a perfect Gaussian random field. So that means there's a lot of cases in which you don't even need anything much more than a power spectrum to get most of the information out of your field. But there is an important exception to that, and that is the intensity mapping experiments that I work on. So this is my 10-minute power spectrum background. Now I'm going to do a brief introduction to line intensity mapping, which I'm just going to write as lim, so I don't have to write long things on the blackboard. So line intensity mapping is a kind of complement to cosmological galaxy surveys, things like BOSS. The basic idea of it is there's a very important and perhaps hard to understand astronomical concept that far away things are hard to see. So normally I point my telescope out at some patch of sky and I identify every object I can that's brighter than whatever the noise threshold of my observation is. And then from the positions of those objects, I can turn that into a density field and compute a power spectrum of it. Or if I'm interested in more traditional kind of galaxy evolution type problems, like trying to understand what the stars and gas clouds are doing in these galaxies, I can construct like a luminosity function of them. Try to understand the galaxies that way. The problem is, as I go farther and farther away, I'm going to, by definition, see fewer and fewer objects at the same level of integration. And that means that out here, one, my sampling of this density field is much sparser, which leads to Poisson error problems. And two, if I'm trying to understand galaxy evolution type problems, then what I'm seeing are the handful of the very brightest objects out in the universe. And if something is in the 99th percentile of luminosity, it's probably not representative of the whole population of galaxies. And I'm phrasing the galaxy evolution in cosmology as separate problems, but really as our cosmological measurements get more and more precise, there's effects like feedback, and these problems actually become more and more coupled together as you try and do these kind of cosmological measurements to higher and higher precision. So the idea of intensity mapping say basically, I'm a cosmologist, I don't care about any individual galaxy. Any individual object can be weird. I want to know the global evolution of the entire universe. And so I say, okay, then I'm going to give up on spending all the time and effort to identify individual objects. I'm going to do a relatively coarse spatial resolution map of the universe in some emission line. And if there happens to be an overdensity of galaxies here, this area is going to be bright. If there's an underdensity of galaxies here, this area is going to be faint. And even though I can't tell you about any individual object, the statistics of those brightness fluctuations will ultimately trace the cosmological density fields, and it will give you the aggregate information about all of these, the luminosity function of all of these sources. And the reason why we do the line intensity mapping, the L in this, is that obviously if I have a spectral line, it emits at a very specific frequency. For most cases, we can approximate it as a delta function in frequency space. And that means that I can tune my observed frequency and very precisely tune the redshift I'm looking at. So for a normal galaxy survey, if I want precise redshifts, I have to get a spectra of all of these galaxies, and that's a very expensive thing to do. Spectroscopic surveys where I have precise redshifts tend to have an order of magnitude or more fewer galaxies, just because of the expense of getting that distance information. Whereas by going after a line, we get that for free. And so, because we're cosmologists, there's a zillion experiments out there doing this kind of measurement. I'm on a handful of them. I could fill this entire blackboard with an alphabet soup of acronyms for all of them. But today I'm going to mostly talk in generalities. So the first thing, of course, the cosmologist does, given all of this, when they make one of these measurements, is they compute a power spectrum.
So before you go on, since I'm more of a spectroscopist,
Yep.
so I'm sure there has to be considerations about which line to choose.
Yes, there
Or
are.
which ranges the redshift range, because H alpha is great, but then it's redshifted,
Yep.
and so forth. And then other lines like oxygen 2 are great, but then they're also metallicity dependent.
Yeah.
So,
So actually, yeah, I guess I specify. So this most popular line, 21 centimeter,
okay.
is the most popular line for this. 21 to the point where line intensity mapping for a long time has basically just been referred to as 21 centimeter
Yes.
cosmology. 21 centimeter has some foreground difficulties that make it actually very hard to do, and more lines are always better when you're doing astronomy. So the most popular ones since then are CO, rotational transitions of carbon monoxide molecules, and there's a fine structure, 158 micron fine structure C+ line. Both of these, glossing over a lot of important details, basically trace star formation activity. The luminosity of one of these lines is very highly correlated with star formation. So if we make a map of one of these, we're basically making a map of high redshift star formation. And star formation is obviously very important to understand how galaxies work. And they are both in many ways observationally easier than 21 centimeter for reasons that I would happy to talk about.
And I assume you're not going to talk about the fact that there can be other lines that come in and contaminate.
I am actually going to
Oh,
talk
you are?
about that fact
Good.
in about 5 minutes.
Good, because that's my favorite.
Continuously about 5 minutes ahead of me. So the power spectrum of one of these surveys, you can write it in a fairly simple form. Basically, everything at the end of the day, the gravitational dynamics of the universe on large scales are dominated by dark matter. So everything on the large scales just follows the power spectrum of dark matter. This is something we have, dynamics codes to calculate to extreme precision all the time. This is not a mystery these days. Galaxies in general are what we call a biased tracer of the dark matter. Just means they show up in the, they don't linearly trace, linearly is the wrong word. They don't exactly trace the dark matter. You tend to have galaxies only in the very highest peaks of the dark matter density field. For a lot of cases, you can approximate that as just a linear increase in the clustering of galaxies compared to dark matter. And then because we're observing a line luminosity, this whole thing is weighted by the mean intensity of the lines we're looking at. This is making the implicit assumption that the line luminosities aren't correlated, but galaxies don't talk to each other on gigaparsec scale, so it's not a terrible approximation. I'm writing a mean intensity as a T for temperature because especially these two tend to be observed in the microwave and radio. Microwave and radio astronomers like to tell you how bright things are as a temperature because it makes some of their math easier. If you're not a radio astronomer, just know that T means how bright something is, because I'm going to use it for the rest of this talk.
In the late time universe, probably C2 might have some weird properties because like there might be no C2 from the most massive galaxy clusters.
Yes, that is a.
Does that change this story, or does local bias like this still work even if there's like really non-trivial things like that going on?
So other than the term I'm about to write, there's a one halo term you can write on this. So effectively the assumption I'm making for the experts in the room is that every dark matter halo has a single point source emitter at the center. In practice, you tend to have a big galaxy in the center and a bunch of small galaxies around the outside. That is something, if you're doing this precisely, you have to model for, and it does become very important in the low redshift universe. I should say, for a lot of the attempts to model these lines, this factor in particular is uncertain at the multiple order of magnitude level. So especially in theory papers, we often neglect stuff like that because it is, the uncertainty due to that is small compared to the other uncertainties in the problems. What we can't neglect though. Yep.
Are you ignoring the redshift space distribution?
For the purposes of this equation, yes. In practice, this is actually a function of k. Oh no. This is actually a function of k and the, well, I guess the red k parallel, k perpendicular, because we actually measure in redshift space, and there's anisotropic effects that come in from that, because from the observational point of view, the line of sight direction is different than the plane of the sky direction. I am also ignoring that right now. What I am not going to ignore, because it is very important for a lot of things, is that even though when I make this measurement, it's going to look like a continuous, and it's going to look something like a cosmic microwave background map, because I don't resolve any individual sources, the emission actually does come from a smoothed over population of discrete sources. And so that means there is Poisson noise in the power spectrum. Effectively, even if there is no large scale correlation between the locations of these galaxies, each galaxy would correlate with itself. And so that gives you a term, I'm just going to write this as a proportionality constant. This gives you as a term that is proportional to the mean square luminosities of my galaxies. It's completely scale independent. It's completely flat, because it's what would happen if there was no cluster on any scales, but it's very important. And so here you can see the Gaussian nature of the power spectrum come into play again, because this mean intensity factor is proportional to the, obviously proportional to the mean luminosity of all of my galaxies times some like number density effects, whatever. And this is related to the variance of my galaxy luminosity function. And so just as before, if this was a Gaussian random field, the power spectrum would be telling me everything. The problem is, unlike nice pristine primordial inflation things, galaxies are very, very, very nonlinear objects. Galaxies are not Gaussians. Smoothing over galaxies, unless I go to extremely large scales, is not going to give me a Gaussian random field. If I have a giant old starburst galaxy in the middle of this pixel, even if there's nothing else there, this pixel could end up being a hugely bright object in its own right. One way to look at that is if I look at the luminosity function of the galaxies, so the number density of galaxies as a function of luminosity, the kind of standard astronomers way to parameterize that is as what's called a Schechter function, which is basically a power law that then has an exponential cutoff at some point. You can see to describe this, I would need an overall amplitude I would need a slope, and I would need to know the location of this cutoff. That is 3 numbers. This, by definition, will only ever give me 2. Therefore, the power spectrum is not containing all of the information about my intensity map. So this is the first half of the problem I'm trying to solve today. That basically power spectra are great for Gaussian random fields, but intensity maps are not Gaussian random fields. So I will pause there for if there are any other questions about that point.
One beautiful thing about that is it means that some aspect of the luminosity function directly creates skewness.
Yes.
And so in principle, you somehow could measure the luminosity function using the skewness, which I've never thought about that.
You are continuing to be about 5 minutes ahead of me.
You were just laying out a beautiful path and I'm just running ahead like a dog.
So the luminosity function should be, we should be able to get it from other ways, right? I mean, from other, I mean, that's, the Schächte with MIT might have, and then I think Mikey worked on the kind of low luminosity N2, right? So,
Well, yeah, there's certainly ways to
so you can,
measure it,
could
but
you kind of constrain the luminosity function independently and then use that?
You could do that, yes. And you would probably want to do both of that and other things in a real analysis. But for the purposes of today, I'm going to talk about, say we're at high enough redshift that we basically don't have direct detected galaxies to do that with.
In the spirit of old man comment, reached a certain age. When I was a grad student, we were told that the C2 line like dominated the luminosity of some large fraction of galaxies when we were, and no one had ever observed it.
Many people have observed it now. But
Yeah,
it
it's
is,
funny,
it
and
is,
it turns out it is a whopping line, although I think it might not be quite as strong as people thought it was.
it doesn't totally dominate the luminosity, but it is, I think it's the brightest line
Mhm.
from most star-forming galaxies, and it's really important for the cooling of gas as it collapses.
Because at 0 or low redshifts, it's very hard to observe.
Yeah.
Because it's 158 microns.
So anyway, okay, so power spectra are great for Gaussian random fields. Intensity maps are not Gaussian random fields. One more question.
Oh, yeah. You started out saying that you're gonna try to solve this with 1-point statistics, but the standard way I think of it is using 3-point statistics to get more non-Gaussian information using the bispectrum. Is that something people do?
Not as much for this. I will also, you are also about 5 minutes. Maybe you're more like 10 minutes ahead of me. So I'm going to describe my second. Well, maybe I should explain the solution to this first, and then I'll describe the second problem. I'll rejigger my order. So yeah, so for things like the CMD, which are almost but not quite Gaussian, the standard way to go after the non-Gaussianity is to construct higher order statistics. So instead of writing 2 deltas in these brackets, maybe you write 3 deltas. And there's a lot of inflation models. So just because of the nature of Gaussian statistics, odd correlators like this will always vanish for a purely Gaussian random field, but they'll be non-zero for a non-Gaussian field. So we can do that for our intensity map. If I wrote like the TTT correlator here, there'd be a bunch of large scale structure terms because large scale structure isn't perfectly Gaussian. But even if I neglect that, this would give me a term proportional to L cubed by the same argument, plus a bunch of large scale structure. I could do a 4-point estimator. This would give me a term proportional to L to the 4th. And I can keep doing that and build up all of the moments of my distribution. Or this is an idea we came up with back when I was in grad school, partially because my advisor thought it would be a way to debug a completely unrelated problem we were having, but that's how PhD advisors work. Instead of just trying to build up all of the moments of the distribution by constructing these increasingly annoying higher point estimators, what if we just look at the probability distribution of brightness temperature in the map? So for the purpose of this talk, if it's a probability distribution, I'm going to try and write it as a curly P to distinguish it from a regular P for a power spectrum. And so basically there is an old radio astronomy technique called Pmd Analysis.
early.
It should
It
now
should
curly
be,
P.
in my notation, it should be a curly P. It was written in text, it's usually not. And I'm not certain if this is an apocryphal story, but The story I've heard of why it's called that is because it stands for probability of deflection, because they used to actually measure the deflection of like a pen on a piece of paper as
Yeah.
they scan the telescope across
Yeah.
the sky.
It was the old Cambridge radio surveys, yeah. And they didn't have the angular resolution, so everything was crowding limited, so
Yeah.
that's all you got.
Yeah, exactly. And this you kind of artificially put yourself in a very similar situation. And so basically what happens here is that if I knew for a fact that I had exactly one galaxy in every pixel of my map, this would just be the luminosity function, modulo some density factors. In practice, what you can do is I can say the full distribution up to some level of approximation, which there are many nonlinear corrections to that I'm going to ignore for now. I can say this is the sum of, given the number of galaxies times the probability of having the number of galaxies. So I have the probability distribution of intensity, given that I know how many galaxies are in a pixel. I multiply that by the chance that there actually are that many galaxies in a pixel. I add that all up, and that gives me a prediction for what the probability distribution of this object is. So we showed back in grad school that this is a very powerful thing to do for intensity mapping, because they aren't just slightly non-Gaussian like the CMB, they are extremely non-Gaussian. We did some simulations to confirm, just by simulating a bajillion things and estimating a covariance matrix, that it does contain very different information from the power spectrum. And you can constrain all three of these numbers using this estimator. Yes.
Isn't there a fourth number that you need for the luminosity function? Is there a low luminosity cutoff?
You usually need a low luminosity cutoff at the level of
Because
sensitivity.
things diverge or something.
Well, I mean, maybe it doesn't matter if the slope's less than 1 or
They
something.
can diverge, yes. For a lot of the sensitivity of current instruments, whether using a power spectrum or this 1-point estimator, this is so far below the noise limit that you basically can't constrain it. But yeah, in practice, this might converge if you don't assume that. So this is great. We have our non-Gaussian random field. We have our statistic against our non-Gaussianity. It's great. That's where I was 3 years ago. But now I'm going to talk about problem number 2, which will hopefully be slightly simpler to introduce. Problem number 2 is that what I've effectively done here is said, I'm going to point my telescope in this direction, and I'm going to record all of the total emission of the sky in that direction at some frequency. I am going to measure T as a function of direction of the sky and nu ops. If I am, pointing my telescope over there and observing at, say, 30 gigahertz, which is where the CO experiments like to survey, I am not just seeing carbon monoxide emitters from redshift 3. I am seeing my line that I want to see. I am also seeing the noise in my telescope, and I am seeing foregrounds or backgrounds or anything of the like. The Milky Way is going to contribute emission. Way down here, I have to look through clouds in the Milky Way. Those have things like dust and synchrotron emission, which will show up in this frequency band. I might also have another set of lines. So actually for C2, if I'm looking at C2 back here, there are actually CO lines that fall into that same frequency space at different redshifts. So 21 centimeter, this is the reason why there have been very few actual 21 centimeter measurements for a lot of work, because for 21 centimeter, the foreground is often 3 to 5 orders of magnitude brighter than the signal, which makes it very hard to get rid of. But what this means is, if I construct a power spectrum estimator, even assuming these things are totally uncorrelated, means I'm going to measure some line power spectrum plus some noise power spectrum plus some foreground power spectrum. And if I don't know exactly what these are, or if I don't have a way to exactly excise these things from my data, these are going to bias any measurement I try to make with this. Now, there are ways to get rid of foregrounds. I can talk about if people want to, but the one of the most robust ways to be confident for especially an initial type measurement is to, instead of doing an autocorrelation like this, where I correlate the same field with itself, do a cross correlation. So let's say, in addition to my smoothed out Galaxy intensity field, let's say I also have some spectroscopically detected galaxies out here.
Different colors of,
I can use
chalk
colored
one.
chalk, yes.
Yeah.
I was saying earlier, it's been like a year since I did a Blackboard talk. Let's say I also have some spectroscopically detected galaxies up here. Or let's say I have an intensity map of a different line covering the same redshift range, or a lensing map, or any other, cosmological observable that I care to lay my hands on. If I write down, say I have two intensity maps for now. If I write down the correlation of line 1 and line 2, the two lines are going to have some non-zero correlation because they are tracing the same dark matter. In most cases, they're going to be coming from exactly the same population of galaxies. But the noise and the foregrounds, as long as those aren't correlated between nu1 and nu2, those will go to 0 because they're completely independent fields. And so a cross correlation estimator is robust to contamination from noise and foregrounds. In practice, we even actually, when we actually measure an auto spectrum in cosmology, we are usually actually measuring a cross power spectrum like this. Even if I don't have any foregrounds, if I don't know my noise precisely, it'll still bias me. So people will usually do is they'll say, take like the first 6 months of my data and the second 6 months of my data on the same field, use those as T1 and T2, and the expectation value of this will still be your regular auto spectrum, but the noise will enter as just an error instead of a bias on that.
I have a question about that.
You sacrifice a square root of 2 in sensitivity, but noise terms that are not correlated between your spring and fall fields.
Right, yeah, but I mean, somehow it's like the autocorrelation ought to add information. Like, because I mean, for one thing, when you do this cross correlation, there must be a way of looking at the cross correlation where you actually estimate what the noise is. Like, somehow it's hard to believe that totally ignoring the autocorrelation.
Yeah, so I think that there are sophisticated versions of this. I mean, first of all, sophisticated versions of this will rarely just do one of these. They'll split
Right.
your data all the ways you can, so you don't lose the square root of 2.
Right.
There are more sophisticated things where you do, yeah, there are more sophisticated treatments. And if you really think you understand your instrument, you can just directly compute an auto spectrum. I tend to work on brand new surveys using this very new observational technique where we have relatively little confidence in how well we understand our instrument. And so when we're trying to make a first detection, this is the safer thing.
Yeah, if you had a survey with thousands of passes, you can build something where each pass is correlated against all other passes. And I think you actually get the full autocorrelation power without the noise.
You do, yeah, as n of these.
Of course,
goes-
the foregrounds will still.
the foregrounds will still be there, yeah, but as n of these internal cross correlation, as n goes to infinity, you get back the original honest, you get back all of the information.
So other ways where you use the cross, as you said, cross correlation between these two kind of lines or aspects, but is there a way that still would give you something interesting
Yes,
about the physics of, for example, if you have,
they're very much.
dust formation versus, star formation versus, metallicity versus.
There very much is. So the cross power spectrum of an intensity map, between two intensity maps, say, I get T1, B1, T2, B2, and then, so first of all, if everything was linear, I would just pick up the two cofactors from my two auto spectra. This is now I'm saying two different lines again, but it might not be exactly that. There could be some scale dependent decorrelation. For example, if, as David was saying, if I have like, one line that likes to live in the central galaxies of clusters and another line that likes to live in the satellites, there would be a scale, like these two lines would decorrelate on small scales. The other thing you get is there's a term proportional to L1, L2. The shot noise term now gives you the average product of these two lines. So it tells you something about how one line varies with respect to the other. So we had a paper, I have a paper in 2019 about how you can probe like AGN feedback with this as one specific example. But once again, so problem number 1 is intensity maps are a non-Gaussian random field. We solved that by doing 1-point statistics. Problem number 2 So we got all this other crap in our map that we don't like. And maybe we want to know something about how two different observables vary with respect to one another. And we can solve those by taking a cross power spectrum. So now the immediately succeeding question is, this is still basically giving me two numbers. Maybe this number and this number are new. I didn't get them from the auto spectrum, but galaxy, I still need more numbers than that to understand how galaxies work. So the question is, can I write down a version of the Pmd analysis that retains both the robustness of the cross power spectrum and some of this extra information? And obviously I wouldn't be standing here if the answer to that was not yes. And so now we are finally going to get to the part where we're going to do some, what still like feels to me like it should be black magic with the convolution theorem to solve both of these problems at once. And this is the part where I'm going to say, again, say that this is not, I'm not claiming that what I'm going to propose here is in any way the optimal procedure to do this, but it's the kind of simplest sounding idea that does work, does appear to work. So yeah. So we're going to
When
take.
it comes to line intensity mapping, it's a low bar on principled data analysis. So
This is why I really like working on it. This is the dirty little secret. We don't know anything, so we don't have to be super
it's the
precise.
Wild West, so
Exactly, it makes it really
great.
fun to be a
Really fun,
theorist.
yeah.
So anyway, so we're going to take advantage of kind of two basic facts. The first one is that if I measure some intensity field that is the sum of two other fields, two other independent fields, that's the independent is important, then the probability distribution of my total intensity is going to be the convolution of the PDFs of the individual fields. This is just a general theorem of probability distributions. Again, only as long as they're independent. This doesn't work if my foregrounds are correlated with my signal somehow. But regular cross correlations don't work then anyway, so say la vie. The other fact is the famous Fourier convolution theorem, which says that if I have the convolution of two PDFs, of any two functions, they don't have to be PDFs. If I Fourier transform that convolution, that turns into the product of the Fourier transforms. This is the Fourier convolution theorem. Again, just a theorem. Everybody okay with theorems? Cool. Now we're going to say, well, if I have a signal and foreground, then my observed PDF is going to be the convolution of my signal and foreground PDFs. If I Fourier transform my PDF, that is going to turn into the product of my signal and foreground PDFs, all just changing the subscripts. Then what I am going to say is, I construct a quantity that I am calling R squiggle. I write down the ratio of, I need to say one more step before I write down R twiddle. The last thing I'm going to say is now I need to make this a cross correlation in some way. I got ahead of myself slightly. So what I'm going to do is instead of just saying P of T, I am going to do something like the probability of brightness temperature given the number of spectroscopic galaxies in my survey. Alternatively, I can write something similar down by saying that doing the 2D probability distribution of two different lines. So now this is where I'm bringing in my cross correlation. If I look at that field I erased where I have both a spectroscopic galaxy survey and an intensity map in the same volume, I can write down the conditional PDF of the brightness of my intensity map given the number of spectroscopic galaxies. Now I'm going to write down a quantity that I'm calling.
Or you could write down the probability, the probability for the C2 deviation given the 21 centimeter amplitude in that same pixel.
Yes, so that's what's equivalent over here. The estimator looks slightly different, but
You're
it's
trying to make a 1-point function that you can apply when you have 2 fields.
exactly, that's exactly, and a 1-point function of 2 fields is a 2D or joint PDF. That's kind of what it is. But now I want to, this quantity, I'm still not going to be able to know it. Like I'm still going to have to deal with my noise and foregrounds in it. This has not yet gotten to the cross correlation point where that's canceled out. But if I write down this quantity, which I define as, say, I Fourier transformed PDF of T given, let's say I split my map into pixels that contain a spectroscopic galaxy and pixels that don't. And let's ignore the possibility that some might have more for now. Divided by the Fourier transform PDF intensity given 0. T twiddle is now the Fourier conjugate of brightness temperature because I am in Fourier conjugate of PDF space. I'm in characteristic function space right now. Well, this will just be my signal PDF multiplied by my noise PDF, or my foreground, or whatever my bad PDF is. But I assume these fields are independent, so this, by definition, does not depend on how many spectroscopic galaxies I have. Then, if I do the ratio, now I have my signal PDF of T twiddle given 0 galaxies, and I again have foreground PDF, which is the same. These two are the same. So the expectation value of this R quantity will be the signal divided by the signal. So be a quantity that only depends on the statistics of my signal, not on the statistics of my foreground. And I have made David facepalm.
You're making me think very hard. This relates somehow to causal inference.
So part of why I wanted to give this talk in front of you before I applied it to data was I have attempted to find things in the literature that do things like this, but I don't necessarily know exactly all of the words that one might use to Google.
It's like when you have a treatment group and a control group, but they're different groups because one is wealthier than the other or whatever, and you want to correct for that. There's these matching procedures where you try to make the populations look the same. And I don't know if this turns into that, but it feels really close.
Yeah, so my basic feeling about this is that there should be problems out there, if not in the astronomy literature, just in the literature that are similar.
Like social sciences.
And so
this
that's
looks like social sciences, right? Because you have you have like low signal to noise in a set of pixels, and you're trying to learn something important from that low signal to noise.
And so this is part of why I'm not claiming this is optimal, because I've been certain all along that some sociologist or somebody has done this better. But what I can say is that this, at least to the degree of accuracy required by intensity mapping, appears to work. So in practice, of course, you don't ever actually measure the PDF, because just like with the power spectrum, this PDF is an ensemble over universes. I actually only have a single block of data. So in practice, these things are actually going to be histograms, or rather, these things are going to be histograms. And so there's some correction terms that have proven to be small in every test I've done so far. What I was planning to do with my last 5 minutes or so was show just a really toy model example of what this actually looks like, to give an idea of the how this might actually work. It might just seems kind of spooky to me.
Before
But
doing
while I
that,
erase,
the T tilde
yes,
is a weird
yes,
quantity, and I feel like doing this Fourier transform of the PDF doesn't feel like it's a necessary, like, do you always have enough of this PDF well-defined that you can do a Fourier transform.
I mean, I
Like
can
sometimes when you measure a power spectrum, it's like, actually, it's hard to Fourier transform that power spectrum.
I mean,
because
I
you
can
have to
type-
extrapolate to do the integral.
I mean, I think the reason why you usually have enough to do anything is because you can always have your noise PDF. Your noise PDF, you measure your noise Gaussian really accurately. So I mean, I can pretty much always write np.histogram, np.fft, which is the level of detail. But yes, because you can always bin your noise PDF up, I think you can usually do that. Whereas the power spectrum, you might only have like 3 bins that you're trying to transform.
Anyway.
Let me do the toy example. For the toy example, I'm going to say, let's say that I have a data set. I'm going to ignore all of the stuff I said earlier about how I really want non-Gaussian data. I'm going to say I have a data where my signal is just some Gaussian distribution with width S, and I'm going to say my foregrounds or my noise are another Gaussian distribution with width sigma n. So what I'm effectively, and then I want to say I want to measure the value of S. So the question I'm effectively asking here is I have a map. It's got a bunch of noise in it. Is there any excess variance in that map above the noise? This is not a physics problem. This is Gaussians are easy to Fourier transform. So if I was just going to measure the convolution of these things, my combined PDF, this is just going to be another Gaussian with width square root S squared plus sigma n squared. And if I don't know sigma n, or if I don't trust my ability to know sigma n, these two will always be perfectly degenerate, and I will never be able to measure S just from the regular one-point statistics of the map. If I do this Fourier transform process, oh wait, sorry, I'm doing the wrong version of this estimator. What I actually need, I'm doing this, sorry, I was debating in my head whether I was going to do the line cross galaxy version of this or the line cross line version of this. What I actually need to do is I actually need to say I have PS of t given 1 is sigma comma S1 PS of t given 0 and sigma given S2. And then any one of these given number of galaxies is going to be SI, but the general point still stands. I still can't, even if I split this up into galaxies versus not, I can't measure either of my S's because there's this quantity.
Sorry, the first argument of the normal is 0. It's a
And
mean of
this
0.
should be T. This
Alright,
is
okay.
this is what happens
Okay.
when you make a last minute decision. Right before
Okay,
you start talking.
okay.
Yeah. But if I go through this Fourier transform, the Fourier transform of Gaussian is just a Gaussian with 1 over this. I can take the ratio of that, and my R twiddle would be, twiddle looks like e to the 1/2 t twiddle S1 squared minus S0 squared. So now I have a quantity where now I have a quantity that only depends on my signal that I can measure directly from my cross correlation without any bias from my noise. You can see that, as tends to happen in a lot of cross correlation analysis, some information has been lost compared to if I could measure this thing perfectly. I can only measure this difference, not either of them individually, but it's still better than the nothing trustworthy I can measure in this case. What this ends up looking like.
Right, because over here you made the foregrounds disappear, but at the expense of only being able to measure certain ratios.
Right, exactly.
So it comes at a cost.
And in the cross correlation equivalent, the version is that cross correlation coefficient. I've lost some of the linearity that I could just infer normally. I have lost because they might not follow the field the exact same way. If I actually plot our, let's say I've written this in such a way that this has a minus sign in front of it. Our tweet twiddle, this is just, the expectation value of this is just a Gaussian. The other thing that I thought would be really scary when I wrote down this ratio thing is putting a data vector with noise in the denominator of something is scary, because there's going to be error on my estimate of this. And if one of those points just happens to be taken arbitrarily close to 0, this ratio will blow up and be terrifying. But what turns out to be nice is that I went through 3 different procedures of figuring out what the error on this quantity should be. I just simulated it to death. I took individual realizations and bootstrapped them, and I made a basically simple binomial estimate of the error on the histogram and propagated that through. And what you find is that at low t twiddle, I get very precise measurements. But then once I hit t twiddle of order 1 over sigma n, that is the point where this thing in the denominator starts being close to 0. But what also happens is the error bars also blow up at that point. So I hit a point where my error bars just start getting really big. And then because the Fourier transform, this is technically the real part. I also have an imaginary part, which in this model is 0. But the 2 sides of this end up being exactly identical because of the symmetries of Fourier transforming a real quantity. So what you basically get is you get something like a window in Fourier transform of temperature space where these things are non-zero, and you can, compute the covariance matrix of these things because they are highly correlated, and do, a at least not terrible Gaussian likelihood estimate. And what we showed in this archive paper is that if I take a model with an actual Schechter function in it, I can, run this through a Fisher forecast, and I can get really nice constraints on my Schechter parameters. Even in the case where my foregrounds are way, way brighter than my signal, and I don't assume I know anything about them. And so with 5 minutes left in the time slot, this is my half-baked Breysse convolution theorem idea. We have some data set from a CO intensive experiment called COMAP that we're actually releasing the first season of data on in like the next 2 weeks. The thing I'm actively working on right now is basically applying a version of this estimator to do the internal approximate the autospectrum version of that to that data. But yeah, this is I'm also in the market for a name for this, because my original version of my 1-point statistics calculation was the voxel intensity distribution, because I can call that VID. My initial name for this thing was the conditional voxel intensity distribution, but then I end up talking about my CVID 2019 paper, and that has become a problem. So yeah.
Thank you. We have more questions. Kate.
So this seems a lot more general than just line intensity mapping. I know you say you can find it in other parts of literature, but could I apply this to my other traces of large field structure? Can they be just discrete tracers? Do I need a field?
Yes, so that is another thing. That is another thing that I would be very interested in hearing. I think there are definitely other places where this could be applied. Basically anywhere where you are interested in this kind of, I really want to call it local non-Gaussianity, but that already means something. But so I've had conversations that, like, Colin Hill has looked at the 1-point statistics of the SC effect, for example. I bet this would be interesting for lensing, or like the relationship between a galaxy field and a lensing field. I bet this would be interesting for
The KSZ and the
KSZ. Yeah, I think there are definitely other things that would be very interesting for. This is just the framework and work I've developed it because there's enough low-hanging fruit in intensity mapping science that I basically haven't stopped thinking about it for 8 years.
What about you implicitly have a pixel here, right? Because you're
Yes.
doing, but in principle, you could put down any kernel. You could be
Yes.
measuring the temperature under any spatial kernel.
Yes. In
And that
principle, you could.
presumably there's a best kernel for any question you're asking probably, and B, probably doing lots of different kernels has some value and creating some space of things.
I bet there would be. So in practice, what I think is going on here is that both the power spectrum or correlation function analysis and this thing are both basically subsets of some, this should be a curly P, of T1, T2, intensity in pixel 1, intensity in pixel 2, and the distance between those two pixels. And then I think basically this smooths R into just the size of a single pixel. The kind of a correlation
Oh,
function is
yeah.
then just the integral, like the variance in this plane.
Yeah, they don't even have to be co-spatial.
Yeah, so I think in principle there is a more general
Yeah, there's a huge
quantity.
space, yeah.
Yeah,
1 point things you could.
This is I guess the full 2-point
Yeah,
distribution.
yeah. I would vertical bar R there, but
Yeah, sure.
actually I was thinking conditioned on R. rather
Conditioned
than
on
P
R.
of
Yeah, okay, yeah, that's probably.
Because R is like a control, but
Yeah,
yeah,
it's probably a
maybe
good
it
way
is,
to
and
say
it
it.
probably does get some kind of.
Yeah,
neat.
and so
Yeah.
yes, so yeah, so and then writing different kernels would just be changing what piece of R you've shrunk it to get this. I know less about how to just write down a theorist expression for this quantity, but in the long term, I really like.
Cool, thank you.
As well, that was awesome.
Yeah.
Stop.
We're all-